All right, let's start by looking at the particular generating functions for induced trivial characters and induced sign characters. These are essentially due to Littlewood and Maris and Watkins. All right, as you can see, Maris and Watkins were not contemporaries of Littlewood. They were much later. And they sort of stated something in their paper, which I'm going to show you, which they said they got the idea from Littlewood's book. Now, neither their paper nor Littlewood's book actually states this theorem, but in both cases it comes so close I feel like I have to attribute it to them. So let's let lambda be a partition. Let's say it has L parts. Then the generating function for the induced trivial character is a sum over all ordered set partitions of type lambda. We take the permanent of the I1 submatrix times the permanent of the I2 submatrix, etc., and multiply those together. And the immanent of the induced sign character is the same thing, but we take determinants of submatrices of X. So the sums are over all ordered set partitions. So I1 disjoint union, I2 disjoint union, etc., up to IL is all the numbers 1 through n, and if we take the cardinalities of each of these, that set of cardinalities is precisely lambda 1, lambda 2, up to lambda L. So before we do this, let's see, I'll remind you also, eta lambda is the trivial character induced from the Young subgroup S lambda to Sn, and eta lambda the induced sign character from S lambda up to Sn. Alright, before we prove this, let's do an example. And also, let me remind you what this notation means. Immanent sub theta of X means we take a sum of theta of W, summing over all W, and we put theta of W next to this permutation monomial x1 W1 through xn Wn. So if we want the value of theta at a particular permutation, we look at the monomial index by that permutation, and its coefficient is the evaluation we want. So, for example, this theorem says that if we want the induced sign character indexed by the partition 2, 1, then that's going to be a sum of products of two determinants. So determinant of the matrix indexed by 1, 2 times the determinant of the matrix indexed by just 3, so it's just a 1 by 1 determinant, just the entry, plus the determinant of the submatrix indexed by 1, 3 times 2, 2 plus the determinant of the matrix indexed by 2, 3. So x2, 2, x2, 3, x3, 2, x3, 3 times x1, 1. So the ordered set partitions I'm using here are 1, 2, 3, 1, 3, 2, and 2, 3, 1. These are all the ordered set partitions of 1, 2, 3, where the first block has 2 letters and the second block has 1 letter. The blocks are disjoint and their union is 1, 2, 3. So if we multiply this out, then we get, let's see, x1, 1, x2, 2, x3, 3. Minus x1, 2, x2, 1, x3, 3. Plus x1, 3, x3, 3, x2, 2. Oops, that's not right. This should be a 1, 1. x1, 1, x3, 3, x2, 2 minus, and this should be a 1, 3. x1, 3, x3, 1, x2, 2. And then here we've got x2, 2, x3, 3, x1, 1. Minus x2, 3, x3, 2. x1, 1. And this is, so these three monomials here are all the same. They're all x1, 1, x2, 2, x3, 3. And these are all different. Minus x1, 2, x2, 1, x3, 3. Minus x1, 3, x2, 2, x3, 1. Minus x1, 1, x2, 3, x3, 2. So this says that epsilon 2, 1 of the identity, 1, 2, 3 is 3. Epsilon 2, 1 of 2, 1, 3, and epsilon 2, 1 of 3, 2, 1, and epsilon 2, 1 of 1, 3, 2 are all negative 1, because their coefficients are negative 1. And of the 6 permutations in S3, only 4 of them appear here. The ones that don't appear have coefficient 0. So epsilon 2, 1 of the permutations that don't appear, 2, 3, 1, and 3, 1, 2 are both 0. So we don't need to use the formula for the induced sign characters. We can read the coefficients off of the monomials here. Alright, now let's look at the proof. And I'll put the claim here again. So let's do eta first, the induced trivial character. So the eta lambda imminent, which records eta lambda of w next to the permutation indexed by w, is equal to a sum over all ordered set partitions permanent of the I1 submatrix, etc., times permanent of the IL submatrix. Alright, so to prove this, let's look at just one ordered set partition and one term in the sum. So let's fix an ordered set partition I1 through IL of type lambda. And let's let U be the permutation we get by writing the blocks of the ordered set partition, each of them with the letters in increasing order. Then U is a minimal element of a coset of the parabolic subgroup S lambda. So we've got increasing sequence, increasing sequence, increasing sequence. So no inversions in any of these blocks. So if we multiply on the left by something that permutes the first lambda 1 letters, it's going to increase the number of inversions. If we multiply by a permutation that permutes the next lambda 2 letters, it's certainly going to increase the number of inversions. So U belongs to the minimal coset representatives S lambda empty set minus. So these are the minimum length representatives of cosets S lambda U. That is, these are all the permutations U such that if you multiply by an element of the Young subgroup, you go up in the Breuil order. So actually there's a bijection between these minimal coset representatives and the set partitions, the ordered set partitions, because each of the elements in this set of minimum length representatives has increasing subsequence, etc., where the increasing subsequences have length lambda 1, lambda 2 up to lambda L. So this map is a bijection from ordered set partitions of type lambda to the minimum coset representatives. Alright, now if we look at the one term corresponding to this partition, so every permutation monomial that comes out of this is going to have first indices u, and second indices we're going to permute the lambda I letters, the first lambda I letters of u, and then the next lambda 2, the first lambda 1 letters of u, and then the next lambda 2 letters of u, and then the next lambda 3 letters of u also, etc. So all of these monomials are going to look like x, u, first indices are u, then the column indices are going to be permutations of u where we're only allowed to permute the first lambda 1 indices amongst themselves, the next lambda 2 indices amongst themselves, etc. Now by the exercise I gave you in the last video, we can take this u and make it a u inverse and put it on the right. So each one of those products of permanence looks like this, and if we take the whole sum of products of permanence over all ordered set partitions of type lambda, by the bijective correspondence above, that's like summing. So the sum over all ordered set partitions I, well, I1 through IL, is a sum over all minimum coset representatives U in S lambda empty set minus the sum of all y in the Young subgroup x e u inverse y u. Now we can look at this as an element of the group algebra acting on xee. So this is sum over u, minimum coset representatives, sum over y in the Young subgroup, u inverse yu, all of this acting on EE. Now let's rewrite this sum as u varies over the minimum coset representatives. We can pull this out because it has nothing to do with y in the Young subgroup. And then we can pull the other u out also. Now, SU is greater than U for all S in the Young subgroup if and only if U inverse S is greater than U inverse for all S in the Young subgroup. So we can swap the U and the U inverse here just by switching left cosets with right cosets. So since this is true, we have a sum over u in S empty set lambda minus u sum of y in the Young subgroup, u inverse x e. Now this element right here, in parentheses, by homework, this is a sum of eta lambda of w over all times w over all w in the symmetric group times x e. So that equals, now if we apply these wx on xee by making it xew, so this is the sum of all w in the symmetric group, eta lambda of w xew, which is what we wanted. That is the eta lambda immanent of x. And similarly, if we look at the determinant of x I1 product up to determinant of x il, that's a sum of sine of y x u y u, where y varies over everything in the Young subgroup. And that means that the sum of products of determinants is a sum over u in the minimum coset representatives, u times sum of sine of y over y in the Young subgroup, u inverse applied to xee, which again, by homework, this part is all equal to a sum over w and Sn induced sign character of ww applied to x. Well, that part is just this applied to xee, which then is a sum of over w and Sn induced sign character of w xew, which is precisely the immanent that we want. The end.